Welcome to this presentation on the electromagnetic mind. Today, we'll explore a fascinating field of research that seeks to understand consciousness from an electromagnetic perspective. This journey takes us from the complex structures and signals within the brain to the nature of consciousness itself. We'll examine the ideas proposed by leading theorists, including Susan Pockett, Shelli Renee Joye, and Johnjoe McFadden, each of whom offers a unique perspective on how electromagnetic fields in the brain may be intrinsically connected to our conscious experience. Through this exploration, we'll delve into questions like, what if consciousness isn't just about neural firing patterns, but is also embedded in the brain's electromagnetic fields? Could these fields provide the missing link between brain activity and the experience of awareness? Join us as we move from the brain's bioelectrical activity to the possibility that consciousness itself is a fundamental electromagnetic phenomenon. To understand the electromagnetic theories of consciousness, we'll start by exploring contributions from some of the key thinkers who have paved the way in this field. This slide represents a roadmap of thought leaders who have developed various theories on how electromagnetic fields could be fundamental to consciousness. 1. Susan Pockett. Susan Pockett is the author of The Nature of Consciousness, a Hypothesis. She argues that consciousness corresponds directly with specific electromagnetic (EM) field patterns in the brain. According to Pockett, these EM fields are not just byproducts of neural activity, but are integral to conscious experience itself. 2. Shelli Renee Joye. In her book The Electromagnetic Brain, EM Field Theories on the Nature of Consciousness, Joye explores the role of EM fields in the mind. She integrates scientific and philosophical perspectives, suggesting that consciousness could emerge from the structured dynamics of electromagnetic fields within the brain. 3. Johnjoe McFadden. Finally, we have Johnjoe McFadden, who developed the conscious electromagnetic information (CEMI) field theory. His theory posits that conscious information is encoded within the EM field generated by neural activity. McFadden presents this as a potential solution to the hard problem of consciousness, suggesting that conscious awareness is a property of the brain's EM field. Each of these theorists provides unique insights into the possibility that consciousness emerges from the brain's electromagnetic field. Their work lays the foundation for understanding how EM fields might bridge the gap between brain activity and subjective experience. Susan Pockett begins her exploration of consciousness by addressing one of the most profound questions in the field: what is consciousness? She focuses on what philosopher David Chalmers calls the hard problem of consciousness. This term refers to the challenge of explaining how subjective experiences, such as the feeling of seeing colors, sensing emotions, or hearing music, emerge from physical processes in the brain. The core of Pockett's hypothesis is that consciousness is not a mysterious or abstract phenomenon, but rather a physical one. Specifically, she proposes that consciousness corresponds to an electromagnetic field generated by the brain's electrical activity. According to her, the brain's EM field might be the physical structure in which conscious experiences are encoded and represented. This idea, that consciousness could be directly linked to a measurable, physical field, forms the central premise of Pockett's work, a theme that she develops and supports throughout her book. At this stage, Pockett explores the current scientific understanding of how the brain functions, focusing on neural activity, synapses, and the processing of information. She delves into the mechanisms by which neural networks transmit electrical impulses, forming the basis of all cognitive and sensory experiences. She introduces two key concepts. 1. Correlates of consciousness. Neuroscientists have identified various neural correlates of consciousness, or NCCs. These are specific brain states that appear to correspond with conscious experiences. For example, certain patterns of brain activation are linked with specific emotions or perceptions. However, as Pockett points out, these correlates alone don't explain the fundamental why or how. That is, they don't clarify why these brain states result in conscious experience. She highlights this gap in neuroscientific understanding as a key issue and suggests that the brain's electromagnetic fields might be the missing link between brain states and subjective awareness. 2. Electrical activity and field generation. This section explains how neurons communicate through electrical signals, creating measurable electromagnetic fields. Pockett argues that these fields are more than mere byproducts of neural activity. Instead, they could be integral to the nature of consciousness itself. According to her hypothesis, these EM fields might serve as the physical basis of conscious experience, transforming brain activity into the subjective phenomena we call consciousness. To understand how EM fields could serve as the basis for consciousness, let's examine how these fields are produced. In the brain, electromagnetic fields result from the movement of ions, mainly sodium and potassium ions, during action potentials and synaptic transmissions. This movement generates localized electric currents, which, when combined across large networks of neurons, form structured EM fields with distinct spatial and temporal patterns. Pockett's hypothesis proposes that these EM field patterns do more than correlate with cognitive activity. Instead, she suggests that each specific EM configuration corresponds directly to a conscious experience. Consciousness, therefore, is encoded in these EM field patterns, forming a continuous, real-time representation of experience. Now, let's look at the scientific evidence Pockett cites to support her hypothesis. Firstly, brain imaging techniques like EEG and MEG show strong correlations between EM field coherence and cognitive states. The more synchronized and organized the EM field, the higher the level of awareness appears to be. Secondly, disrupting EM fields with techniques like transcranial magnetic stimulation, or TMS, can alter or even disrupt consciousness, indicating that these fields play a functional role. Finally, research suggests that EM fields can actually influence neuron firing and synaptic plasticity, which could create feedback loops essential for sustaining conscious states. This evidence points toward the idea that EM fields are more than just byproducts. They may actively shape and reflect conscious experience. Pockett's hypothesis has some profound philosophical implications. If consciousness truly exists within the brain's EM field, then it becomes a physical entity, subject to measurement and perhaps manipulation. This changes how we think about the mind and self. Consciousness would no longer be an abstract product of computation but an emergent property of a physical field. Additionally, if EM fields can hold conscious content, this raises questions about the possibility of consciousness existing in other EM field structures, even outside biological brains. Could certain types of artificial or environmental EM fields ever generate conscious experience? Pockett's hypothesis opens the door to new perspectives on the nature of consciousness. Pockett's hypothesis stands out when compared to more neuron-centric theories like integrated information theory and global workspace theory. While these theories describe how information is processed and distributed across neural networks, they struggle to address the hard problem of consciousness, explaining how these processes translate into subjective experience. Pockett's view differs by suggesting that consciousness is not produced by neural connections alone. Instead, the EM field generated by these connections may serve as the true substrate of consciousness. This perspective also offers a natural solution to the binding problem. Rather than stitching together fragmented neural activities, the EM field provides a cohesive, continuous structure that directly encodes and unifies perception. Of course, Pockett's hypothesis is not without its challenges. One of the main criticisms is the difficulty in isolating EM fields as the sole cause of consciousness. The brain's EM fields are complex and influenced by many factors, making it challenging to isolate what might be a consciousness-specific aspect of these fields. Another issue is the lack of direct causal evidence. While correlations exist, we don't yet have proof that EM fields are directly responsible for consciousness. Finally, technological limitations make it difficult to measure and precisely manipulate EM fields in relation to subjective experience, which limits our ability to test this hypothesis experimentally. In conclusion, Susan Pockett's electromagnetic field hypothesis provides a novel framework for understanding consciousness as a physical phenomenon. By proposing that consciousness exists within the brain's EM field, Pockett redefines it as a tangible, measurable entity. Moving forward, advances in neuroimaging, EM field modulation techniques, and studies focused on EM fields' causal relationship with consciousness could bring us closer to validating, or refining, this hypothesis. Pockett's work invites us to explore consciousness not just as an abstract process, but as a potentially measurable phenomenon grounded in the brain's physical EM field. Now that we've explored Susan Pockett's hypothesis, let's turn to Johnjoe McFadden's conscious electromagnetic information, CEMI, field theory. McFadden builds on the idea that consciousness is connected to the brain's electromagnetic fields, but he takes it a step further. His theory, known as CEMI, proposes that consciousness isn't just an effect of EM fields, but is actively encoded within them. According to McFadden, the brain's EM field plays a central role in processing information and in creating conscious awareness. This approach suggests that EM fields are not passive reflections of brain activity but are crucial components in the mechanism of consciousness, potentially providing a bridge for solving the hard problem by linking brain activity with conscious experience. McFadden's CEMI theory posits that the brain's electromagnetic field is more than a passive byproduct, it actually functions as a medium for encoding information. In this view, the EM field created by neurons doesn't just sit alongside neural processes, it actively interacts with them, influencing neuron firing and establishing feedback loops within neural networks. Through these feedback loops, the EM field integrates and organizes neural information, creating a cohesive conscious experience. McFadden suggests that it's this dynamic interplay between neurons and the EM field that gives rise to conscious awareness, positioning the EM field as an essential, active participant in the brain's cognitive processes. McFadden supports his CEMI theory with several lines of scientific evidence. First, studies on electromagnetic field modulation techniques, such as transcranial magnetic stimulation, show that altering the brain's EM field can change states of consciousness, suggesting that EM fields play an active role in awareness. Additionally, research shows that EM fields can directly influence neuron firing rates and promote synchrony within neural networks, especially during higher cognitive functions. These findings support McFadden's idea that the brain's EM field serves as a real-time medium for processing conscious information, directly interacting with the neural network to sustain conscious states. One of the significant contributions of McFadden's CEMI theory is its potential to solve the binding problem. The binding problem refers to the question of how separate neural processes across different brain regions combine into a unified, continuous experience. McFadden's theory suggests that the EM field generated by neural activity acts as a single, unified substrate that integrates information from all parts of the brain. This unified EM field enables the brain to produce a seamless, cohesive experience of consciousness, solving the binding problem naturally by allowing separate neural events to be experienced as one continuous flow. McFadden's CEMI theory also introduces profound philosophical implications. By suggesting that consciousness is encoded in the brain's electromagnetic field, the theory implies that consciousness is a physical phenomenon, something that can potentially be measured, influenced, or even manipulated. This challenges traditional views of the mind and suggests that consciousness may not be confined to biological neural circuits alone. If EM fields can support conscious information, could artificial or synthetic EM fields exhibit conscious properties? McFadden's CEMI theory opens the door to exploring consciousness as a broader phenomenon, potentially existing beyond biological brains. Pockett and McFadden both view the brain's EM field as key to consciousness, but differ in approach. Pockett argues that consciousness aligns with specific EM field patterns from neural activity, reflecting conscious experiences. In contrast, McFadden's CEMI theory suggests that consciousness is encoded within the EM field, which then interacts with neural processes to produce conscious states. McFadden's theory, however, faces challenges. Proving EM fields directly cause consciousness is difficult, as these fields are complex and influenced by many factors, which makes isolating their role in consciousness challenging. Technological limitations also prevent the precise manipulation of EM fields necessary for thoroughly testing the CEMI theory. By integrating Pockett's and McFadden's perspectives, we get a fuller view of consciousness as an electromagnetic phenomenon. Pockett focuses on EM field patterns correlated with neural activity, while McFadden emphasizes conscious information encoded within the EM field. Together, these theories suggest a layered model of consciousness, potentially leading to a unified framework with future research. Ultimately, Pockett and McFadden reimagine consciousness as a measurable feature within the brain's EM field, encouraging a view of consciousness as a tangible part of the brain's electromagnetic landscape. With advances in neuroimaging, we may soon test these ideas, exploring the EM field's role in consciousness more deeply.